Hi, my name is Wijntjes, and this is my Lab 3, Magnetic Field of Permanent Dipole Magnets. As an introduction, the purpose of this lab was to measure the distance dependence of the magnetic field due to a bar magnet. I created a computational model based off the Beer's law in GlowScript to visually represent the magnetic field of the bar magnet at on-axis, perpendicular, and off-axis observation locations. I compared experimental values to the expected values derived from the computational model. For the results, I calculated experimental value for distance dependence n was negative 3.1199, while the theoretical value is negative 3. I also compared the predicted value for the magnetic field of the bar magnet 45 degrees off axis to my observed value I got while conducting my experiment. Some of the physics principles highlighted in this lab were the magnitude of the magnetic field of a bar magnet is equal to K times R to the N, R being the distance from the magnet to the observation location. The magnitude of the magnetic field of a bar magnet decreases the observation location is moved further away from the bar magnet. K is a combination of constants and parameters that were unchanged during the experiment, and measuring the magnitude of the magnetic field of a bar magnet at different distances from the bar magnet allowed us to determine a value for N. Earth also produces a magnetic field, so it was important to compensate for Earth's magnetic field when trying to measure the magnetic field of the bar magnet. A derivation of the Beer's law was also used to determine the magnetic field of a dipole. The bar magnet was a permanent dipole. For the setup, I compensated for magnetic north first by aligning my phone with north using the Teslameter app. I knew it was north when the x component of the magnetic field on the app read 0 microtau. I then aligned a meter stick against the bottom of my phone. This was east to west. I then found the magnetometer chip in my phone by orienting the bar magnet so that it was aligned with my meter stick. I then slid my phone along the line perpendicular to the meter stick until the x component was at a max and the y component was at a min. I then rotated it 90 degrees and slid my phone perpendicular to the tape I had put down before and got an x component min and a y component max, and then taped again. This was my magnetometer chip. It was in the upper corner of my phone. I then measured and observed for on axis. As the magnetometer moved close to the magnet, the measured x component of the magnetic field increased. When the magnetometer was far from the magnet, it measured a near zero magnetic field in the x direction. I recorded distances where the x component of the magnetic field of the bar magnet was equal to 20 microtau, 70 microtau, 120 microtau, 170 microtau, and 220 microtau. These distances allowed me to determine a distance dependence n. I then measured off-axis magnetic field. I did this by finding a distance d perp along east to west where the magnitude of the net magnetic field of the bar magnet was equal to 100 microtau. I then moved my phone this distance and along another meter stick that was perpendicular to the first one and determined where my experimental B value was at 45 degrees and got a value. This is my data analysis. I used a logarithmic function ln b x is equal to ln k plus n ln r. ln bx and ln r vary and n and k are constants. The magnetic field decreases as distance decreases, and I expected n to be negative. N was negative 3.1199. This is my magnetic moment calculation. I used this value in my GlowScript code and derived it from the function to extract distance dependence from my experimental values. This was some of my GlowScript code where I first represented the magnet as a cylinder. I then entered the magnetic moment I got on the previous slide down here. I then wrote a function for the magnetic field of the bar magnet at different locations using the previous derivation of the Beer's law. I then entered on axis in perpendicular locations, and then I used my function to calculate the magnetic field at these different locations. I then drew arrows to represent these magnetic fields at the different observation locations. You can see here in my computational model, the blue arrows represent the perpendicular observation locations. The orange arrows represent the magnetic field at on-axis locations. I then also have a green arrow to represent my off-axis location, B 45 degrees. I then printed the values for the magnetic field at all these different locations in my output of my computational model. This is my percent error. There's a 4% error for my observed versus predicted n value. This is my percent error for my B 45 degrees predicted versus observed. This was much larger than my percent error for my n value, and means that there were some discrepancies in my experiment, maybe because I didn't either align my meter sticks correctly for the second part of the experiment or my phone was slightly tilted. This is my conclusion. If I hadn't compensated for magnetic north, the graphed function would have looked the same as the results, but they would have been shifted by the same magnitude. There would have been a larger margin of error in the lab. The difference between the theoretical and experimental values would have also probably been larger. If I were to stick two identical magnets together end to end and run the experiment, the magnetic field at each location would have doubled. Magnets are identical and oriented the same way, so the magnetic fields would have added together instead of offsetting each other. This increased the strength of the magnetic field by increasing the number of magnets. Thank you.